Welcome to this video on solving cubic and quartic equations with complex numbers. So first thing, let's look at the two types. So cubic of the form az cubed plus bz squared plus cz plus d equals 0, like this, is generally going to have three roots. So obviously in the past you would have already dealt with, so let me just put three roots. You would have already dealt with them when you have three real roots. And those are the ones you're used to dealing with. For within complex numbers, you're going to get one real root and then one pair of complex conjugate pair, so it's going to be two complex roots. So just repeat. So cubic, you're going to have three roots. All three roots could be real, and like I said, these are the ones you would have dealt with within your normal pure maths, or within this further maths unit where we're looking at complex numbers. You're going to have one real root and two complex roots, and these complex roots will be a conjugate pair. So you know once you've got one, you've got the other one. So it makes your life so much easier. Now, with a quartic is obviously the higher power is for that. So with a quartic, you're going to get four roots. Now, obviously, all four roots could be real. So for real roots, or how we tend to do this within our further maths, which obviously involving the complex numbers, is that you're likely to get either two real, two complex, and this will obviously be, one complex conjugate pair, or you're going to get four complex roots, and this will be two pairs. So two complex conjugate pairs. Sorry, I find it sometimes hard to talk when I'm concentrated on spelling certain words. So conjugate there, I kind of have to say it in my head to spell it out. So just in case you're wondering why sometimes I am pausing while I'm writing. So these are the scenarios we get. Obviously the three roots, the four roots, the three real roots, the four real roots there. You don't tend to see these questions within the further pure one because the focus is on complex numbers. So you're far more likely to see, for cubic, one real with one pair of complex, one complex conjugate pair, say it properly. And with the quadratic, so the quartic, we would expect to see either two real and then one complex conjugate pair, or two complex conjugate pairs, and that's what we're likely to see. But other than that, there's not a huge amount of difference between these and the quadratics in the last video. Okay, obviously they will involve a little bit more working out, a little bit more work because of the increased number of roots, but otherwise the processes are not that dissimilar from each other. So let's jump into a couple of examples. Let's start off with a cubic. So here we're given that 2 is a root of the equation f of z, find k and solve completely. So if 2 is a root, that basically means that z equals 2 is one of our roots. So for the first one, this means that then f of 2 should be equal to 0. Okay, so my f of 2 will just mean that I'm substituting 2 into everything within this cubic. So that's 2 cubed minus 6 times 2 squared. Hopefully my 2's do look a little bit different from my z's. So then plus 2k minus 26, and of course this will equal 0. So skipping a few lines, simplified it down to 2k minus 42 equals 0. So 2k is going to equal 42. K will be equal to 21. So now we've got our f of z is z cubed minus 6z squared plus 21z and then minus 26. Now that will enable us to find or completely solve this equation. Now if 2 is a root, that is us saying that z is equal to 2, therefore z minus 2 will be a factor. So this is a factor of our f of z. So from this we can use factor theorem or long division to be able to split it up and get the quadratic. I'll do both ways with this one. Let me just make a little bit of room. Now I'm sure most of you will be pretty familiar with doing this, so feel free to fast forward or skip this bit, but I will just quickly walk through the long division. So obviously dividing my z cubed by z is going to give me z squared, and then I'm multiplying. So z squared times z cubed, and then z squared times minus 2 2z. And then what I'm actually doing is I'm taking away. What I tend to do is I just change both signs and then I add. I've always done it that way. That's why I was taught, so that's why I kind of still do it this way, I guess. Just find it easier. So now this is the value we're dealing with, so z will divide into this, leaving me with minus 4z, and then taking this and multiplying again by both of these values is going to give me, let's actually bring down this plus 21. So z squared times minus 4z times z minus 4z squared, that's always going to work out like that. Minus 4z times minus 2 is going to be plus 8z. And of course then we are taking away, which I just change the signs and then I add. Like I said, I just find it easier that way. But I'm guessing that is probably because that's just the way I was taught how to do this. Now the 13z, so this is going to give me plus 13 up here, and then multiplying by the 13, so we get 13 times z, 13z, and 13 times minus 2 is minus 26, and again change my signs and add, and we get 0. And there we have it. So we've now got, for our f of z, which was originally, in fact, let me just copy, quick shortcut there. So now this is equal to z minus 2 and z squared minus 4z plus 13. Okay, now what I'm going to do here is I'm just going to pause and I'm just going to talk through another way in which you can get to this point before then we continue any further. And I'll do this in a different colour just to kind of show the difference. Now, alternative method is obviously start off with our cubic. We know that z minus 2 is a factor. So z minus 2 there. And then we know that this is going to be multiplied by a quadratic to be able to get our cubic. So this is az squared plus bz plus c. And all I really want to do here is compare each of my coefficients. So there's a couple of ways in which you can do this. You can expand and simplify, then compare. Or you can do them individually. I'll show you kind of both ways. So if I was just going to expand, I'm going to multiply first everything by z, and then everything by minus 2. So we get az cubed plus bz squared plus cz, and then we get minus 2az squared minus 2bz minus 2c. And then this means we get az cubed, and then if I look in at my my z squareds, we get b minus 2az squared. Let's take the minus out here, or take the plus out again. For c's we get, for z's we get c minus 2b z, and then we get just the minus 2c at the end. And that's of course z cubed minus 6z squared plus 21z minus 26. So all we're doing is we're just comparing now. So looking at, sorry, that should be z cubed, shouldn't it? From here, silly mistake there. So looking at our z cubed, we can see that a equals 1. Then we can see, looking at our squareds, we can see that that is now b minus 2a is equal to minus 6. Looking at our z's, we can see that c minus 2b equals 21. And we can see essentially minus 26 equals that minus 2c. So I'm just going to put 2c equals 26 there. So we know a is 1. So we get b minus 2 equals minus 6. So b is equal to minus 4. So c, this is going to become plus 8 equals 21. So c equals 13 there, or we could get c from this one. So obviously we only need it once there, so either of those. So that's the other way of doing it. If you don't want to do long division, you can compare, and obviously you can expand and simplify. I tend to do the same kind of thing as this, except for like this step. I don't actually do this part of it. I effectively do this part in my head, and I just jump to this step. So when I'm doing this, I just go, right, z cubed is obviously 1 there, yeah, and then how do I get z cubed? There's only one way, it's these two multiplied together, so it's going to give me az cubed, yeah, so it's just a. So that's my a equals 1 straight away. Then when I'm looking at the z squared, that's minus 6 there on the left. And then how do I get z squared? Well, z times this. So it's going to give me bz squared, so just b. And then minus 2 times this z squared. So it's going to be minus 2a. So I'm just looking at the coefficients. And obviously, since we already worked out a, again, we know how this works. So b here is minus 4. And then again, I don't need to use this one. I just jump straight into the constant. So the constant here is minus 26. And the only way to get a constant out of all of this is minus 2 times c. So minus 2c, therefore c is 13. So that's how I go about doing it. So that's how I speed things up. It's just a comparison. Yeah. So remembering, obviously, there's only one way of making the cubed in this one, but there'll be two ways of making your terms in the middle, so to speak. So in this case, your z squared and your z. Okay. So just remembering that there's two ways of making those is quite easy. But in this case, like I said, you only actually need to use the z squared, and then you can jump to the last one. So you can see that if you can do it this way, you can just visualize it and just quickly go through it, just looking at the coefficients of z cubed, z squared, and the constant there. You'll be able to get these values really quickly, and obviously then it means you get down to the same point. So that should be a z. It looks a bit like a 2, where we get z minus 2, and obviously a is 1, b was minus 4, and c was 13. So obviously just substituting then your a, b, and c there. Okay, so hopefully now you're clear on, use whichever method you prefer. Get comfortable with more than one method, I'd always say. And anyway, we'll go from there. So we've got our answer. Well, our answer so far. What we need to do now is, since obviously we're solving f of z is equal to 0, we know our z minus 2, so we've got, if I just rewrite it up here, z minus 2, and we got z squared minus 4z plus 13, and that obviously equals 0. So now we need to solve this quadratic. Just trying to concentrate to make sure my z's look like z's and not number 2's. So we're solving this. There's more than one way of solving this quadratic equation. You could use completing the square, you could use the formula. It's totally up to you. I'm going to use the completing the square just because this is a nice even number, so it should be pretty straightforward. So z plus 2 squared minus 4 plus 13. So z plus 2 squared is equal to this. Z plus 2 squared equals minus 9. Plus 2 squared equals the square root then of minus 9. You remember from previous ones, it's obviously plus or minus there. So this is going to be, sorry, get rid of that squared. Z plus 2 is equal to plus or minus 3i. So there we have it. Z is minus 2 plus or minus 3i. And that's our complex conjugate pair there. Or the other solutions would be minus 2 plus 3i and minus 2 minus 3i. And there we have it. And obviously z equaling 2 was that first one, which was already given to us. I'll pop that one there at the end in brackets. And that's it, solving a cubic. Easy. There isn't really any different. They're always going to be one real and a pair of complex numbers, so it should be quite straightforward. Let's look at a quartic though now. So how you approach this question is going to be slightly different depending on what you're given. If you're given a real root, a real value, then you know you're going to get 2 real values and 1 complex conjugate pair. If you're given a complex number, then that's the bit where you're not sure. So obviously you get the other pair, the other value, but you could have another pair of complex numbers, or you could have 2 real numbers. So you're not really going to know until you start to solve it. But for this one, you know, we've got our first one, z is going to be 2 plus 3i, which means that this will be 2 minus 3i. So that's our one pair. Now, as I said, now we don't know. The other ones could be 2 real or 1 additional pair. Okay, so, you know, that's what we've got to go with. I'll rewrite that as just 2 complex. So, you know, it could be 2 real or 2 complex numbers. And like I said, if we started with bracket there. If we'd started with a real number, we would have likely ended up with a complex conjugate pair. Obviously, you couldn't still have all 4 roots real, but like I said, in FP1 they're testing you on your knowledge of complex numbers and things, so I don't think you're ever going to get a question with 4 real roots. But I wouldn't run it past Edexcel, or if you're using any other boards, who knows. So first thing is to take our pair here and write it as a quadratic so that we can get one of the main factors. Because what we're basically looking at right now is that we get z4 plus 2z cubed minus z squared plus 38z plus 130. This is equal to z minus 2 plus 3i and z minus 2 minus 3i. And then of course we have a z squared plus bz plus c. Remember that this is obviously because these, if you think of making these equal to 0, is the easiest way to think about it. You take in both of these to the other side, so that's where you got minus and minus. So all we really need to do is work this out as a quadratic, and then from there then we can use long division or factor theorem to find these values here. Okay, so let's do that now. Alternatively, if you remember from the previous video, we can use effectively alpha and beta. If I pop this up in purple now, so if you remember, z minus alpha times z minus beta equals 0, and this would be z squared minus alpha plus beta plus alpha times beta. So if you think of like one of these being alpha and one being beta, or here they are up here, then this can make your life quite easy, quite a lot easier, I would say. So let's go alpha plus beta is going to be 4, and alpha times beta is going to be 4 minus 9i squared. Yeah, obviously it's like completing, it's like the difference of 2 squares when you're multiplying these, isn't it? Or this will be 4 plus 9, which is 13, and that, you know, is really quick to do. So what I can do now is I can replace this. If I pop it straight into brackets, we've got z squared minus alpha plus beta was 4. Oh, sorry, that would have been 4z plus alpha times beta, which is 13. And that makes our life so much easier, doesn't it? So using this method, sorry I just messed up the Z, but using this method just makes your life so much easier and it's so much quicker. So I would really highly recommend you learn that because it's a really good shortcut for you. So like I said, now we've got two options. Long division, so you know z squared minus 4z plus 13 is going to go into our full Quartic here. That's a lot to write down. Or using the factor theorem. Can't even spell theorem today. Okay, so you know, whichever method you prefer. I tend to use the factor theorem a lot on this, although I do like long division. Generally, it really just depends on how quick or what the question is looking like. You know, if I look at this, you know, we're comparing this with this, so I can see straight away that A is going to be equal to 1. It's the only way I can get my z to the power of 4. To get z cubed, so looking here, we know that the coefficient on the left is just 2. And look at how I can get to z cubed on the right. I can do z squared times bz, so that's just going to be b, the coefficient there. Or I can do minus 4z times az squared, so that's minus 4a. Okay, we know a is 1, so we got 2 equals b minus 4, so b is going to be equal to 6 there. And then to find c, I'm just going to look at the coefficient 130 here, and then the only way to get the coefficient will be 13 times c, therefore c is equal to 10. So like I said, you know, it's really quick, really easy if you can do that bit, you know, just getting used to working out just the coefficients for each of the terms you need to be able to find your A, B and C. Okay, I will quickly just do the long division, but I'm going to fast forward it this time. As you can see, both end up with the same solution there. So substituting our values for A, B and C in will give us this. Now, we already know the roots to this one, which we've got here, so we just need to find the roots to this quadratic. So now we've got z squared plus 6z plus 10. And we're going to make that equal to 0. Again, use the formula, complete the square, it's totally up to you. I personally use completing the square if this is an even number, or I jump straight in with the formula if this is odd, sometimes just to avoid the fractions. But that choice, you know, is totally up to you. I actually think that a lot of the time you do get nice numbers, so a lot of the time this will be an even number. Well, if it's going to be a complex number, it's often an even number. But like I said before, you know, you just don't know. But that's what I would do. I would use completing the square if that z term there is even, otherwise I would use the formula. Of course, you can use your calculator as well, but you should show a lot of you working out. So here we can see, it's at this point we know whether this is going to be complex or not. So you can see it's going to be +1 there. This ended up being a positive number. You know, when it goes to the next side, it's going to be negative. So you know then it's going to be a complex. Whereas if this was negative, you know it would end up being real. So we've got z plus 3 squared equals -1. Z plus 3, obviously taking the square root there, that's just going to be I. Square root of -1 is I. So we get z is equal to -3. So that should be plus or minus I. Plus or minus I. So all of my solutions, well, actually, let's just write this one. So this one is, you know, the other two solutions would be -3 plus I and -3 minus I. When we talk about all our solutions, I would write them all down. So we get 2 plus 3I, 2 minus 3I, -3 plus I, -3 minus I. So in this case, we've ended up with 4 complex solutions there, complex values. So 2 pairs of complex, sorry, 2 complex conjugate pairs, I should say it that way around. And that's all there is to it. You know, at this point we could have ended up, like I said, this could have been real values. So we could have had a pair and 2 real. That is the other possible scenario here, really. We could have obviously all 4 real, but unlikely in FP1. So a bit long in terms of the explanations at the beginning of this video today, but hopefully it was clear enough for you guys to understand. Let me know any problems with that, or if you cannot hear me clear enough. I am suffering with a bit of a cough at the moment, so my voice is a little bit on its way. And yeah, don't forget to like, subscribe, tell your friends. Any kind of help you can give me just will potentially open me up to a bit more time to be able to spend on YouTube in the future. So anyway, I've put together a few questions on cubics and quartics. Have a go at them. I will go through the answers as usual. I'll go through them quickly, fast forward if it's quite straightforward, but I will talk through any bits that I feel might not be. But I think in this case, there's nothing too dissimilar to these examples. Okay, this is not too difficult, but since it's a little bit different, I thought I'd talk you through it. So we know that 6 is a root and 3 plus I is a root. So we know that 6, 3 plus I, and 3 minus I are the roots of this equation. And from here we can effectively do this in probably a couple of ways. You could go about setting up an equation, so something like z minus 6, z minus 3 plus I, and z minus 3 minus I, and expanding that, giving you a cubic in which then you can compare. Alternatively, you can use your alpha and your beta. So your alpha is 3 plus I, your beta is 3 minus I, to find the quadratic part first. This is how I would probably do it, because your alpha plus beta is always nice and easy. It's going to be 6, and alpha times beta is going to be 9 minus I squared. And obviously I squared is minus 1, so it's 9 plus 1, which is 10. And that then means that we get z squared minus our alpha plus beta, so minus 6z plus our 10. And that then means that our g of z should be z minus 6 multiplied by z squared minus 6z plus 10, and of course that is z cubed minus 12z squared plus cz plus d equals 0. So all you want to do here is either expand this, then compare, or just compare the terms that you need. So we want the value in front of the z. So to get that, it's going to be z times 10. So just looking at the coefficient, that's just 10. Or minus 6 times minus 6z. So it's going to give me 36z. So just the positive 36 there. And of course that is going to be the c. So c is going to be 46. And then for d is just the constant. So minus 6 and 10. And when I multiply those, it gives me minus 60. And it's going to be equal to d, so d is equal to minus 60. So doing it visually by comparing coefficients is far quicker and easier than doing the expansion, but both are valid. You know, if you're unsure, expand it. Safest option, yeah? But what you really want to do is get a bit of confidence in this, because, and I say this on a lot of my videos, time is your biggest enemy in the exam, and any minutes you can save, seconds even, on these types of questions just gives you that little bit of time for some of the more challenging questions towards the end of the paper. Okay, so I would really recommend you practice this quite a lot so that you're able to take these shorter routes towards the answer. This has a lot of similarities with the last question, but I thought I would talk through it again. So we want to write it obviously in this form. So z squared minus 9, z squared plus bz plus c, and of course this is equal to z to the power 4 minus 12z cubed plus 31z squared plus 108z minus 360. So again, compare your coefficients. Obviously we don't need to worry about the letter A here, as that's just 1 and we can see it there anyway. So moving on to this one, B. So the coefficient of, well, we could pick anything really. Let's go with the coefficient. So cube is probably the easiest one to start off with. So to get the cube would be z squared times bz. So that's bz cubed, so the coefficient is b. And then the other way of making, oh, there is no other way, is there? of course, of making it. So it's just going to be b, and minus 12 on the other side. Of course, there's no other way in this one because this one is as a quadratic rather than individual, like a z plus 3 and a z minus 3. So yeah, b is minus 12. Now we want to find out what c is, so that's just going to be the constant. So minus 9 times c minus 9c on the left of the equals. Constant on the right is minus 360. Divide by minus 9 and we get a positive 40 there. Nice and, I think, straightforward. So that was obviously part A. Once you got these, finding the solutions to part B are really straightforward. It's just finding this quadratic equal to 0 and solve. So I'll do that with a bit of speed. Again, this is not super difficult at all, but maybe it's easier to talk it through. So for part A, if 2 minus 3i is one root, then 2 plus 3i is the other root there, because of it's obviously a complex conjugate pair. Now, if I think of, alpha being 2 minus 3i, beta being 2 plus 3i, then alpha plus beta is going to be 4, and alpha times beta is going to be 4 minus 9i squared, which is obviously 4 plus 9 or 13. That means that my quadratic is going to be z squared minus 4z plus 13. Now that's I've kind of jumped ahead here, haven't I? That's not what we needed to do for A. Apologies. Actually, I can go from this point. It doesn't really make a difference. So let's go z squared minus 4z plus 13. And this is equal to az squared minus 6. Minus plus bz plus c. What am I doing? Started to read this out then. That's what we're trying to show, isn't it? And that, of course, is z to the power 4 minus 10 z cubed plus 71 z squared plus q z plus 442. So what we really want to do here is find our a, b and c, and then we can go on and find q. So a, b and c, obviously a is going to be equal to 1 straight away. We know that because the z to the power 4 is 1. Looking at my cubes, this is going to be b minus 4a, and that's going to be equal to minus 10. So obviously we got that, gives me a cube, and these two multiplied give me a cube there. A is 1, so we've got b minus 4 equals minus 10. B is equal to minus 6, just as we would expect. Now we expect c to be 34. So looking at c, easiest way is with the constant. So 13 times c, 13c is equal to 442. And a quick check on the calculator gives me 34. So therefore then I can say that it is a factor, yeah, because we've got our z squared minus 4z plus 13 multiplied by z squared minus 6z plus 34, and that of course is equal to all of this. So you can say hence z squared minus 6z plus 34 is a factor. In this case, I don't think there was another solution or way of doing this because of that q, but if any of you do think of another way, just let me know in the comments down below. Anyway, from this point we can find q relatively easy. So q is just the coefficient of z here, so we just want the coefficient of z from the left side. So if I look at how I get the coefficient of z, would be this term multiplied by 34, so minus 4 times 34. I'll put it like this just so it's a little bit easier to follow. The other way is the 13 times the minus 6z there. So it's also the 13 times by the minus 6, and that's obviously going to equal to my q. And that means that q is going to be equal to minus 214. Okay, very straightforward there. Nice easy part B. Final bit now is to solve completely. So all we really need to do, obviously this one came from this root here, so all we need to do is solve this quadratic. Nice easy solve, and as we've got this even value for z, we will complete the square. Hopefully you found today's video useful. Don't forget to like, subscribe, comment, share, and so on. And I'll see you in the next video where we look at Unit 2 or Chapter 2 of this unit, roots of quadratic equations.